Good day, everyone. This is Guangrui Zhang from the Ocean University of China. My topic is multi-channel convolutional neural network-based soft sensing approach for measuring moisture content in tobacco drying processes. My speak will fall into four parts of content. The first is the research background, and then we design some research objectives. The third part is the introduction of the research methodology and the experimental result analysis. And finally, we will meet the research conclusions. In cigarette industry, the drying phase of the tobacco contains warming and humidifying, drying, and winnowing. The moisture content of the outlet tobacco will be measured after the winnowing machine. However, there is a delay time caused by the measurement of the moisture content. During the delay period, preventive and remedial actions are rarely conducted effectively, and the tobacco is frequently over-dried or over-wet. The moisture measurement is difficult to be directly conducted, especially when the tobacco is still in the drying machine. Hence, we need to develop a new approach that can not only meet the requirement of the measurement precision, but also meet the requirement for timeliness. Which means we use a new approach to eliminate the detection delay of the moisture content measurement. Here is the hypothetical ideas of our work. Firstly, we acquire the data from the production practice, and then we select relative parameters and try to find the suitable model structure for this work. And then we use the model to extract the features from the raw data. And then a reliable model is built to make the online prediction for the moisture content. As you can see in the flowchart, the upper side is the current method that is used to measure the moisture content level in tobacco. The delay time T before the moisture measuring process is 5 minutes in average, which means we need to wait at least 5 minutes to get the moisture content measuring data, and we still need to spend some time on analyzing and detecting anomaly in the tobacco based on our expertise. This costs a lot of time. So, in our method, we use a data processing block and a fully trained MCCNN to replace the time-costing processes. Okay, let's see how our method works. We all know that the process data we get from the production line may be a huge, diverse time series data. This data set may be not suitable for use directly to the machine learning model. So first, we manually removed some of the process variables that contributed nothing for the predictive modeling process. Then, the features is selected automatically according to the impact weight of parameters, which use the out-of-bag data error as the index. The second step is to convert the data from a linear time series format into a matrixed image-like format. Hence, this data can be used as a neural network input. So we first number each parameter sequentially, and then we intercept these data into slices. These slices can be used as a input for the neural network. Well, the figure shows that how the data slices looks like in the data space. You can see that each two-dimensional data vector is with a size of 42 by 42, and the three channels can be presented as here like XYZ, YZX, and ZXY. The transformed dataset will then be used as the input of the proposed MCCNN model. As you can see in the figure, the MCCNN model consists of three convolutional layers, two pooling layers, and two prediction layers. The kernel size of the convolutional layer C1 is 7 by 7, and the kernel size of C3 is 3 by 3, and C5 is also 3 by 3. And for the pooling layer size, S2 is a layer with a kernel size of 2 by 2, S4 is 2 by 2 as well. The detailed configuration of the proposed MCCN model is listed in Table 2. By using this modeling method, we can extract meaningful state spatial coupling information and time sequential features using the convolutional and pooling layers. We have carried out experiments to compare the performance between our proposed MCCN model and other models. The data used for the experiments is from the cigarette manufacturing factory's real-world production data. Three batches data are randomly selected, one normal instance, and two aberrant productions. The first comparison is between the proposed MCCN model and the standard CNN-based model. You can see in the figure that in the normal instance, the prediction result of MCCN is fitting the actual values well, and the SCCN model's result is not fit the actual values. In the abnormal instance 1, the MCCN model's result is with a little error, and the SCCN model's result is drifting from the actual values. In abnormal instance 2, you can see both methods fit the actual values, but the result of SCCN has a big variant range, which is not as stable as the result of MCCNN. Table 3 shows the prediction results analysis of all three cases. You can see in the table that MCCNN has better MAE and RMSEs in all of these three instances. Then the proposed approach is compared against that of other state-of-the-art networks, which is ANN, SVR, RNN, and RMAX. You can see in the figure that our MCCNN method is the most stable method that fits all along the whole process to the actual values. We have concluded all these experimental results of these 5 models into the lower part of this figure. You can see that the proposed MCCN model has the lowest MAE and RMSE, which means the proposed model has better performance than other compared state-of-the-art networks. In our guess, this is because that the multi-channel two-dimensional vector can extract the spatial and sequential features more comprehensively from the raw data, which leads to a better modeling result. Here you can see the mean values of MEAE and RMSE of MCCNN are the smallest, and then the ANN, RMOX, and RNN. SVR has the worst performance. Okay, now we can meet the conclusions here that in our work, meaningful time sequential and state spatial coupling information was retrieved comprehensively by multiple convolution and pooling layers. The MCCN model's prediction performance is validated by comparison tests with other prediction models using the real production data. The detection delay is eliminated and the response time for exceptions can be considerably reduced using soft sensing modeling and multi-channel feature extraction. The proposed method introduces a new research strategy for addressing the issue of important production indicators that may be difficult to identify. Okay, my speak ends here. That's all of my share. Thank you for listening.